Hello everyone, welcome to the first tutorial class of this course. I am Anirban Santara. I am a PhD student in the Department of Computer Science and Engineering of IIT Kharagpur and a TA for this course. So in these tutorial classes, I am going to take you through step-by-step hands-on problem solving in the area of machine learning. So in the first tutorial class, we are going to concentrate on linear regression, logistic regression and decision trees. And we will use decision trees for regression and classification, and these are going to be the first steps that will give you a picture or give you an idea of how problem solving really occurs in real life machine learning applications. So the platform which we are going to use is Python based toolbox called Scikit Learn. So this particular toolbox is very popular in the industry as well as in the academia and has implementations of a huge number of machine learning algorithms, and we are going to use this particular library in most parts of our course. So in this particular tutorial, we are going to use two things from the linear model part of the Scikit Learn toolbox. So the first thing will be linear regression, second will be logistic regression, and then from the tree module of this particular toolbox we are going to use decision tree regressor and decision tree classifier. Let's come to linear regression first. So linear regression is all about approximating a linear function on your data. So given a data, you're going to fit a model, and this model is limited by the family of linear functions of the input features. So the first thing which we will do in this tutorial is create a synthetic data set. So why do we use a synthetic data set? Just to keep things simple. So our synthetic data set has been made using the function which you can see on the slide. So it's a very easy function, and the third part of the function is actually Gaussian noise, which gives some randomness to the data and a feel of what real life data sets actually look like. So the first step in any machine learning problem solving is to visualize the data set, and this actually gives a nice picture of how complex the problem actually is and like how to exactly go about solving the problem. So visualization is important. And the second step in any machine learning application is to split the data set which is available to us into three fragments: the training data set, the validation set, and the test set. So the protocol is to train the model on the training set, and after every episode of training, in order to evaluate how good the algorithm would actually generalize in the real world, we are going to evaluate the model on the validation set. And after every episode of learning, we go about doing one phase of evaluation on the validation set, and we come back and tune the hyperparameters of the system. Like we can change the kind of features we are using. We may like to change certain model architectures and say number of nodes in or number of trees in an ensemble. So or number of nodes in a neural network, and these things are the hyperparameters which are not optimized directly by the learning algorithm, but those hyperparameters have to be observed based on the model's performance on the validation data, or how good it actually generalizes to real world. So that's why we need the validation set. And finally, after all the training has been done, all the tuning of the architecture has been done, we take the test set and we find the performance of the model on the test set. And this particular performance which we get, it's actually supposed to be reported as a measure of actual generalization of the model, because this particular test set was not shown to the model at any phase of its training, neither during its parameter learning nor during its hyperparameter tuning. So this actually gives a feel of what a set of unseen examples or unseen cases may look like. So that's why we need to do this kind of a split of the data that's available to us into training, validation, and test sets. And it's a general practice to have 70% of the data aside as training set and the rest 30% is divided into validation and test set. So that's what we do here. So the next step is to fit our linear model onto the training set, and over here we first invoke the linear regression the class, okay, and we create an object of this particular class, and this particular class has a number of has all necessary functions that are required for working with linear regression models, okay, and that's it. And we first like create copies of our training set. The X train and Y train are the training features, the inputs, and the labels, and we reshape them into the particular convention which is necessary for the linear regression object, and we create copies of these data sets because it tends to overwrite the examples if we do not do it. So that's why. So first we do this, and first the data is ready, so that's what we have in the second line. So X train for line fitting and Y train for line fitting, they are the input features, and targets, that is the desired outputs, of course, respectively. And next we go for the training part, and in this particular episode what do? We at this particular step we we invoke model.fit, this function. So this particular function does a squared error minimization on the training set. So what does it do? For every single training example, it calculates the prediction for the model, and then it finds out what is the amount of deviation of this predicted value from the desired value, which is also given to the model. And now this deviation or the error is first squared so that it becomes insensitive to the sign, and then it is summed over the entire training set, and this particular error is the squared error that we are talking about, and this error is minimized through gradient descent learning. And finally we get a model which minimizes the squared error. And so here we see that the model has learned to fit a line to the data, and this line minimizes the squared error on the training set, and you can see that it passes nicely through the distribution of samples. And the fourth step is evaluation of the model. So in this particular step, what do? We find out how good the trained model generalizes. So because it all matters to us, what all matters to us is how good the model would perform on some unknown task. Okay, so when the model, it doesn't matter to us how good the model would perform on some seen examples or the examples from the training side, which we already know. We already know the desired outputs, the correct outputs for all of those examples. They don't matter to us anymore. What matters to us is how good the model would perform when it is sent out to the world, to the unknown world, and asked to perform. So that's what we talk. What is meant by the generalization performance, and this generalization performance is to be measured next. So what do? We find out the mean squared errors for the validation set and the test set, okay, and those numbers can be calculated in using the code that's given. All right, so yeah, that was the end of the linear regression part, and all the code and instructions and explanations will be provided to you through an IPython notebook, which will be provided to you via the portal for this particular course on NPTEL, and currently they are also on GitHub, and I think that they will we will preserve these IPython notebooks on our GitHub page as well, and those links will be provided in the course website. All right, so you would be able to directly use that particular notebook, and you execute the cells one by one. So each cell describes one particular step in the learning procedure, so in the entire procedure. So the entire procedure is broken up into steps, and each step is within each cell, and you execute a cell and it will execute the particular action that's required. All right, so that's going to be really convenient for you people to practice and understand how a thing is done. So next we come to logistic regression. So logistic regression is all about classification using a linear decision boundary. Now you can look up on the web and find out how exactly this classification via a linear decision boundary happens using logistic regression. Rather, I can just say in a few words that a logistic regression model would try to so it's inherently a binary classifier, so it's a two-class classifier, and it can be trained to output a probability for the two classes. Given a particular input example, it can output the probability of it belonging to either class 0 or class 1, say, so like either true or false. And now you can like threshold the output into at like say 0.5, and the output which a logistic regression unit would give is between 0 and 1. So if you threshold that value at 0.5, you'll get a classification output. All right, so this is how logistic regression works. So you can also look up on the web. So logistic regression performs classification via a linear decision boundary, and we are going to use a very popular data set. It's called the iris data set, as in this particular example. So this data set is actually a data set of iris flowers. So these flowers fall into these plants come in 3 different species, 3 different kinds of flowers. So the task is to classify these flowers on the basis of just 4 of their features, with the sepal length, sepal width, petal length, and petal width. And based on these 4 features, you have to classify the flowers into one of the 3 different species. So this is the task, all right. But to keep it simple and easy to visualize and appreciate, I have decided to reduce the complexity of the data set a bit. So what we are going to do, we are just going to take up 2 features of the data, with the sepal length and sepal width only, and just consider 2 classes out of 3 possible classes of flowers. We are going to take 2 classes of the flowers. So the simplification is this. So we use only 2 input features, the first 2 and the first 2 classes. All right. So we do the same exercise as before. We split the data into training, validation, and test sets as is necessary, and then we fit the logistic regression model. So we invoke the logistic regression class and create an object, and then we do a model.fit. So this does the minimum error approximation. Okay, so this particular algorithm will minimize the classification error, and you can find the full documentation on the official website of Scikit Learn, right? So once this model is trained, you can find that this model creates a linear decision boundary. So as I said before, so the 2 different classes are easily linearly separable in this case, and that's why it's possible to draw such a beautiful decision boundary which correctly divides the entire feature space into 2 fragments, right? So as you can see there, the blue region belongs to class 0 according to the model, and the orange one belongs to class 1. Okay. So finally we evaluate the model, and we find that we have 0% misclassification error both on validation and test sets. So like it completely generalizes according to as far as we know by according to the data that has been provided to us. So it's just because of the case that we were fortunate to have the 2 classes that we picked to be linearly separable in the particular feature space that we chose, and that is not the case in most of the real world situations. But just to keep things simple and just to give you people an idea of how logistic regression works, I chose this example, right? So next we enter decision tree regression. So decision trees are piecewise linear models. Alright, so the linear regression and logistic regression, they were like single line fitting models. Alright, at least the variant that I showed you, the particular model that I demonstrated in this tutorial. But a decision tree tries to learn a set of if-else conditions. Alright, if-then-else conditions. So if the input be in a particular range of the feature space or in a particular place of the feature space, then it is going to fit one particular line to the data. So it's a piecewise linear model, right? And we use the same data set, same synthetic data set that we used in the linear regression example. And finally we fit the model. So we invoke the decision tree regressor class, we create an object of that class, and we fit the model by minimizing the again the amount of deviation which we have from the true values. And what we are going to do in this particular section of the tutorial is understand how we can engineer the maximum depth parameter of our decision tree to control the amount of bias and variance that's there in the model. So we see that the leftmost example that you see, that has a maximum depth of 1. So it's just a single if-else condition. So if the data be lesser than 1, then it's using one particular line, and if it be greater than 1, then it's using another line. Okay, and it's a very simple model. That's the simplest possible. So maximum depth equal to 1. We can see that both the training error and the generalization error, which is given by the training, and the validation and the test errors are high. Okay, and that's why, and while if we go to maximum depth equal to 3, then we can see that we have a piecewise linear model which fits really closely to the data, but maybe it fits just well, which will come to the next slide and we will discuss about this. So which one fits the best? Whereas if we increase the maximum depth to 10, then you can see that this tries to fit the data really closely, and this is not at all sustainable or at all generalizable, because you can see that it's trying to hug on to every single point of the example set, of the training set, and most of these points are noisy because we explicitly superimposed some Gaussian noise on the data. So this is not at all encourageable. So that's why we should, this particular model has very high variance, and we should be able to identify this overfitting happening and choose a maximum depth which is lesser than this value. So the next slide, this curve shows the variation of training, validation and test errors with maximum depth. Alright, so as you can see that for maximum depth equal to 3, up to maximum depth equal to 3 rather, training, validation and test errors, all of them keep decreasing. Alright, or at least they are non-increasing, whereas if as soon as we increase the maximum depth parameter beyond 3, the model starts overfitting, and that's clear because the training error decreases, whereas the validation and test errors tend to increase. All right, so this is what is done in practical machine learning. So we would rather choose, for making the model which is going to be deployed, we are going to choose a maximum depth of 2 or 3. Rather, 2 is a far safer option, because we don't really want the model to fit snugly on the data, because we want to keep it loose so that it kind of fits well on the data. All right, so it kind of fits well on the training data, as well as it generalizes well in the real world. So our preferred choice of max depth would be either 2 or 3 in this case. So next, let us look at the application of decision trees in classification. So decision trees learn piecewise linear decision boundaries. So a single logistic regression classifier would learn a single line as a decision boundary, whereas decision trees can like learn piecewise linear models. So what do we mean by that? So we mean by that the feature space is going to be divided into small volumes, and within each single volume the decision tree is going to learn one particular hyperplane, which is the generalization of a line, and that's the general linear function. So this particular kind of behavior happens when decision trees are used in classification, and that's what we are going to do next. So we are going to use the entire of iris dataset here. So iris dataset has 4 input features and 3 output classes, and do the same kind of training, validation and test splitting. And next we create an object of the decision tree classifier class, and we fit the model. All right, we fit the model. Yes. Okay, and this also minimizes the classification error. So this is one piece of code, and the source of this code is also given in the IPython notebook, which will be also presented on the course website. You can find it out there. So this is a nice way of visualizing the decision tree, at what particular decision node what kind of decision is getting learned. And as you can see that finally the model learns to each of these leaves has a Gini index of 0. So the Gini index or Gini coefficient, yes, the Gini coefficient is a measure of how homogeneous a cluster is. So a Gini index or Gini coefficient of 0.0 means that the cluster of inputs, or the set of inputs that are coming to that particular leaf node, are all belonging to one single class. So they are completely homogeneous. So when you like push in one example, an unknown example, through the decision tree, and it lands up in one particular leaf, you are 100% sure that what particular class it's going to be, because each leaf corresponds to one class. So this is like one kind of decision tree making procedure, or making philosophy, and there can be other variants as well. So we will discuss it in the next classes, or we will supply links to you, web links, which give better description of how complicated decision trees and decision forests are learned to classify the data well. So next is evaluation of the model. All right, and we do it in the same way as we had done in the last 3 examples, and we get a validation set error of 12%, because see, the previous one which we did, it was a simplified version of the iris dataset, and the beauty of the iris dataset is that the first and the second classes, they are linearly separable, but they are not linearly separable with the third class. So as soon as the third class comes in, so it's difficult to fit a linear decision boundary, and that's why we get some non-zero validation and validation error. In this case, the test error is luckily 0, just because the third class had come in and the sets were not anymore linearly separable. Okay, and there is a nice way of visualizing decision boundaries learned at every single of these nodes. So every single node learns to, or the decision node learns to learns a particular decision rule. So it learns to choose certain features and splits on those features on that particular chosen feature axis, which increases the homogeneity in the training, in the amount of in the clusters going into the children nodes of that particular decision node. And and so we have 12% validation error in this example. So you can try out these models using other input data, and we can discuss the performances on the course forum. All right, thank you so much. So thank you so much for attending my first ever video recording. Thank you so much. See you guys in the next video, and we will be discussing principal components analysis and feature selection, which also form very crucial aspects of practical machine learning. So bye bye, see you next time.